All right. Hey, everybody. So today we're doing topic 41, deep neural networks. So we're just going to go into a little bit more of all of the different hyperparameters that are involved in different neural networks. And then we'll talk about images. We'll start to talk about images. Just as a reminder, tomorrow I'll be doing the official project kickoff. Part of that, I'll talk about better ways to collaborate. I do have a couple teams of 3. Again, it's really just to make everyone's workload lighter because we do go straight into capstones right after this project. So I do want to give you all a little lighter of a workload. So tomorrow will be the project kickoff. Friday we'll continue with the end of neural networks. I'll also, at the end of next week, when we're wrapping up our projects, I'll start sending out capstone resources so that you all can start thinking about what you'll be doing for your 4-week-long project. Cool. Quick reminders, leave your stand-ups on the Slack channel if you haven't already, as well as blogs. And again, if you don't hear back from a project partner by the end of today, please ping me and let me know. I can try and rally, and if any shuffling has to be done, I'll do that too. But with that, any questions before I begin? All right, so today we're talking about deep neural networks, about tuning neural networks. Now, tomorrow I'll actually show you the grids, not tomorrow, but on Friday, I'll show you all the grid search equivalent to neural networks. But first, we're going to talk about all of the different things that you can tune within a neural network. After that, we'll talk about convolutional neural networks, which if you actually take a look at our curriculum on Canvas, convolutional neural networks are actually in the appendix. However, if you're working on the image classification project, which about half of you are, if you're working on the image classification project, convolutional neural networks are going to give you much better results. The only difference, and you'll see, is just changing one layer of your neural network. We'll get into it in a little bit. But if you don't end up using convolutional neural networks as part of your project, that's okay as well, because technically it is in the appendix. But I do want to talk about what a convolutional neural network is and how that can really increase the performance of your image classification project. All right, so to start, we're going to talk about some of the hyperparameters that you can tune within a neural network. Now, this is very, very broad because these things that I'm going to talk about, nodes and layers, activation functions, loss functions, optimizers, learning rates, and regularization, these are things that can exist in any kind of neural network. So you'll start to see that you can add or adjust these parameters no matter what kind of neural network you're doing. Maybe some of the more specific neural networks, you have slightly different things that you want to tune, but for the most part, any forward-feeding neural network, you will see these parameters come up. Then, as I mentioned, we're going to talk about convolutional and pooling layers. These are going to be relevant for image classification. So the thing about neural networks, and we sort of saw yesterday, right? Yesterday, we were doing a classification problem on that Pima Indians data set, and there was only 8 features. However, there were 2,000 parameters to tune. So because of that, we lose all interpretability. We had very, very little information on what was helping our model predict well, what were important features or what were strong coefficients. You actually cannot get that information out of a neural network at this stage. So when it comes to tuning a neural network, it's a lot of trial and error, especially as we're first getting introduced to neural networks. I think it's really only with a lot more experience working with neural networks and getting into the math of backpropagation, the math of activation functions, so on and so forth, then you'll start to be able to make more educated guesses on what your hyperparameters should be. But for a lot of bootcamp neural network projects, is really going to look a lot like this, where you're just going to test a bunch of different things. But you can kind of narrow down the things to test based on what you're seeing with your results. So those are the things I'm going to talk to today. Again, I'm not going to go over exactly tuning in this session, just talking about what are the things that you can tune. On Friday is when I'll talk about the grid search equivalent. There are actually 2 different ways that you can do grid search for a neural network. And if any of y'all are doing, if for you all that are doing the neural network project, I would like to see some tuning. Very similar to this last project, at least one model being fine-tuned. All right, so to start, the first thing that you can adjust your neural network for is nodes and layers. Now, this doesn't really matter what kind of layers that we're dealing with. Yesterday, we talked about just dense layers. So every node is just a regular perceptron. So things that you can do, one, you can add layers, as you saw in our, actually, let me pull up the last one that we were looking at. So yesterday's notebook, we were doing a model with 2 dense layers. See, we were adding our first input dense layer, and then we had an additional dense layer. So this was 2 dense layers. If I wanted even more granularity for my model, I could add another dense layer to see how that helps. Maybe it leads to overfitting. We can see that in our results. Maybe it helps our overall predictive power. Very, very difficult to say, but you can experiment with adding these layers. Other than that, you can also play around with the number of nodes or perceptrons per dense layer. Actually, you'll see that it's not just dense layers. We're going to talk about a couple other kinds of layers later for images. But for any of these, the number of perceptrons or the number of nodes that you have is actually quite arbitrary. Typically what you do in traditional neural network structure, you start with a fairly large number and then you start to narrow down. But it's truly, truly arbitrary. So yeah, for many problems, you can start with just 1 or 2 hidden layers, it'll work just fine. But for more complex problems, and by complex, we mean that if you have less separable data, or if you have a lot of features, you can gradually ramp up the number of hidden layers until your model starts to show signs of overfitting, or you start to see a divergence in your training and testing scores. For very complex tasks like image classification without convolutional layers, we're going to talk about convolutional layers at the end of this notebook. You might need, or you will need, dozens of layers, because if you imagine every single pixel is going to be a feature. So you're going to need dozens of layers. So you can play around with the number of hidden layers as well as the number of neurons per layer. So it is very, so the number of neurons for your input and output layers, they do depend on the data and the test. So for example, your input dimensions are determined by the number of columns that you have, and your output layer for classification depends on how many classes you're dealing with. We'll talk about these like final activation functions next. But for example, in here, input dimension is 8. And then your output layer, because in this case, we were just doing binary classification, we only need 1 node that is forced into a sigmoid output, meaning your output from this layer will be between 0 and 1, and it will just round off to 0 or 1 to do your classification. So in general, you will get more bang for your buck by adding on more layers versus adding more neurons, which makes sense because when you add a layer, you're adding like X number of neurons at a time versus just increasing neurons per layer. Cool. I think I mentioned this earlier as well. For hidden layers, a common practice is to create a funnel that goes fewer and fewer neurons per layer. Any questions about this? I will say this is fairly arbitrary. If you see that your model isn't improving, one thing that you can quickly do is just add another layer and see if it learns quicker. All right. Same for neurons as well. Okay, so next is activation function. So as you notice, every single layer that we're adding has some sort of activation function. And activation functions serve several purposes. One, it can actually force your outputs to be in a certain form. For example, for our output layer, the activation function that you use for your output layer is highly dependent on the task that you're trying to perform with your neural network. So here, because we're doing binary classification, it's got to be a sigmoid function or any sort of function that will force your values to be between 0 and 1. Here, as I mentioned yesterday, ReLU, which stands for rectified linear unit, that activation function has proven to do very well. It's also one of the more efficient activation functions. And very similar to what I was talking about yesterday, what the activation function does is after you sum together your variable values and the weights that your model has tuned, you sum them together, add your bias or intercept, and then you pass that value through the activation function, and that goes on to the next layer or goes into your output. So it's sort of like a level of transformation before it goes into the next output. So some common activation functions, you have your sigmoid function. Again, as you see here, it forces all values to be between 0 and 1. You have hyperbolic tangent, which also has a very, very similar function of keeping your values between -1 and 1. And then you have ReLU that looks like this. And ReLU is cool because if, and how you kind of think about ReLU, if your output is 0 or less than 0, your neuron will actually not be fired, if that makes sense. So your output will actually be 0 from that neuron. So how you read these activation functions is you have some sort of X value, and then you take a look to see what the corresponding Y value is. So for example, let's just say after you sum together your weights and your variable values for classification, and you end up with like a value over here, you'll trace up and you'll get a value of, like, in this case, let's say 0.9. And this 0.9 will get rounded up to 1 to get your classification result of 1. Now for this, as long as your values are 0 or lower, you will actually get nothing output from your neuron. Your output will be 0, actually. And so this actually helps your neural network become a little bit more efficient, because any neurons that are not producing numbers or results will actually not have to be computed in future layers. So as you can see here, from any value between 0 and up, you'll just have a linear transformation. So as you can see here, the relationship here is a 1-to-1. So if my value here is 0.5, my output value will be 0.5 as well. And that's why ReLU is used very often, because it is a very easy to use activation function, because it's 0, if it's less than 0, or the value itself, as long as it's above 0. Because there is this issue of you might lose a lot of data, sometimes you might use either leaky ReLU or exponential ReLU. As you can see, they're just slightly different. Instead of your value always being 0, you can have slightly negative values here, slightly negative values over here. I would switch from ReLU to any one of these if you see underfitting happening. And whether it's underfitting because of this or because of not enough layers, that's really something you have to trial and error. Cool. Let me clear this, zoom back out. Any questions about this so far? Okay, neat. So for output layers, these are some of the common activation functions used. So as I mentioned, for binary classification problems, a sigmoid activation to coerce values between 0 and 1. Multi-class classification, you want to use softmax activation because it produces a non-negative vector that sums to 1. So let's say you have 5 classes, you're actually going to get an output of 5 numbers that is basically the probabilities associated with that data point belonging to each class. And so that's how it decides on the classification as well. So yeah, non-negative vector that sums to 1, which is basically probabilities of your test point belonging to the different classes. Next, for regression, you can either use linear activation, and linear activation is literally, it's not in this diagram over here, but linear activation function is literally like this. So whatever it sums to, that will just be your output. And then finally, you can also use ReLU if you want for linear. In terms of activation functions for hidden layers, I've linked a bunch of more detailed articles here that you can read to figure out what activation function you might want to use. So for hidden layers, there are a couple go-tos. So for example, I talked about how ReLU is typically what's used because it is very efficient. But next, there are some reasons why you wouldn't use some others. So it also has to do with the calculus of it and something about your learning rate. So first of all, sigmoids are not often used because it has a small maximum derivative and thus only propagates a small amount of error each time, leading to slow learning. So what that means is, because backpropagation, similar to gradient descent, has to do with the slope of your cost function, because that's how your model is learning. With a sigmoid activation function, the idea here is that your gradient is never large, meaning that at no point, or the maximum gradient is kind of around, oops, let me draw it out over here. The maximum gradient is kind of over here. And by maximum gradient, I mean the maximum rate of change. like as you see here, the slope at these ends are almost flat. And it does get a little bit more steep, and then it starts to flatten out. So the thing about sigmoid is that its maximum gradient is bounded. So therefore the learning can be quite slow if you use a sigmoid as your hidden layers activation functions. I believe tan-H has a similar issue. So this small derivative slow learning issue is known as the vanishing gradient problem. It just means that your models will take very, very long to train and learn its best parameters. So tan-H, yep, mathematically quite similar to the sigmoid function. If you see hyperbolic tangent, you'll see it's spelled TANH if you were to use it in a model. So that, as you can see, looks very, very similar. Its maximum gradient is bounded as well. So yeah. ReLU generally works well because its gradient is always 1 as long as the input is positive, and negative inputs going to 0 can make your network lighter. As I mentioned, the fact that these values, as long as the sum outputs are 0 or less, it'll actually not have to do that computation for that particular node or perceptron. So it actually makes your network a little bit lighter, and it is more efficient for the neurons that are firing. Any questions about activation functions? As you see over here, I'm using ReLU in both the hidden layers and then a sigmoid at the end, because sigmoid matches the tasks that I'm trying to, the classification test that I'm trying to do. Okay, so next we have loss functions. And where do loss functions come in? Loss functions come in when you're compiling your model, because this tells your model, overall, given all of my layers and everything, how will I figure out how well my model is doing? And so it's pretty much a cost function. Loss function and cost function can kind of be used interchangeably. So from this, loss functions also kind of depend on the task at hand. Like, as you know, when you're doing classification, your cost functions can be like entropy for decision trees, or for logistic regression, it's kind of an MLE gradient descent procedure. And for regression, you would use your mean squared error. So yeah, loss functions are akin to cost functions. We are trying to minimize in gradient descent. So for regression problems, Keras has mean squared error or mean absolute error or mean squared logarithmic error that you can use as loss functions. For binary classification, you should use binary cross entropy because it's sort of a measure of misclassifications versus correctly classified values. And then for multi-class, pretty much the same, but just categorical cross entropy. So basically we'll calculate very similar to actually entropy itself, the same entropy that we were computing within our decision trees cost function. Basically misclassified over correctly classified, or the purity of classification. So again, I've linked another article. A lot of these things, I would say like each of these sub categories that we're going through can pretty much be like an entire week's worth of material. So we are going through this very, very quickly. So if this is all like a lot and going over your heads, that is honestly to be expected. Okay, so that's loss functions, and that's like with your model as a whole, how does the training algorithm know how well it's doing or if it's getting better or not? So also kind of with loss functions, there are optimizers, and optimizers you also define in your compilation step. And there are different kinds of optimizers. It's basically how it learns or the way or the path it takes to learn the best parameters. So there's a couple here. Yeah, different methods or paths that your neural network can take to find optimal values. So experimentally, Adam, which is the one that I have over here, has proven to be the best one to use. And Adam just comes from adaptive moment estimation. I have an article linked about Adam as well. And some of the most common optimizers that you can use. First, RMS-prop, which basically maintains per parameter learning rates adapted based on the average of recent weight updates. So what that means is, let's say you're tuning 10 different hyperparameters. And then you see that, let's say that 2 of those hyperparameters, they're already pretty close to their optimal values. They will actually slow down the learning rate of those 2 those two features, those two parameters, so that it doesn't like overshoot its value. And it knows that maybe some other parameters, maybe 3 other parameters are still working through its learning, so they won't adjust the learning rate for those. So RMS prop basically allows for those differences in learning rates across parameters, and it'll automatically adjust for that. AdaGrad does pretty much the same thing, but it has been designed to work better on problems with sparse gradients. The sparse gradients, you can think of natural language processing, you know, how the data for NLP can be very sparse because, as I mentioned, not every, in a bag of words data set, not every data point has every word involved, so you have a lot of zeros. So AdaGrad has been experimentally shown to perform better on sparse data. Computer vision, we'll actually get into that in a little bit as well. And then Adam is sort of like a happy medium between the two. Instead of adapting learning rates based on the average first moment, it makes use of the average of the second moments and the gradient. So basically it is saying like, all right, if one of my features seems to not be learning very much anymore, it's gonna doubly make sure that the rate of the learning is not slowing down by too much or is not speeding up by too much, so that it does again. Again, it's just a more adaptive learning rate, basically, for each parameter. So those are optimizers. Typically, if you use Adam, it's fine. The only difference, if you change your optimizers, you might see your model converge faster or slower. It really depends on how different your parameters are and how different they are from their initial values. And the initial values, if you remember from yesterday, initial values are randomized to start. So you might see very, very different performance, even running the same model over and over again. Okay, so something else that you can do, and this by default, you actually don't really have to define. And as you see here, I'm not defining learning rate anywhere here, but you can if you want. So learning rate is something that you can define when you compile your model with the optimizer. And the optimizers usually change up the learning rates anyways, right? Like what I was saying earlier, these optimizers will adjust the learning rates automatically. So this is just the initial learning rate. So typically I actually don't really set these initial learning rates unless you see that nothing is happening at the very, maybe like first 50 epochs, nothing is happening. What you could do is set a high learning rate to start, but you again do run the risk of overtraining your model or overshooting optimal values. So this I actually would suggest that you don't have to do anything about unless you've tried a bunch of things and nothing is working. So you have to be very careful with learning rates. If you set too low, training will eventually converge, but it'll be very slow. If you set it too high, it might diverge. That means it might completely overshoot its optimal parameters. And as a result, the neuron might not be helpful anymore. And if you set it slightly too high, it'll converge but miss the local optimum. It'll basically do that. If you imagine a cost curve where you want to get to the minimum value, it's going to do that like bouncing back and forth of that, which can also slow down your training time. Cool. But learning rate, not really something that you have to explicitly incorporate because of the optimizers that are defined. Cool. Regularization is also something that you can do in neural networks. As we saw, I think with these results over here, or do I still have that graph? Okay, as you can see over here, some overfitting is already happening. And with so many parameters, let's see, like this one had, okay, 277 parameters for like an 8 feature problem is a lot. And model complexity usually comes hand in hand with overfitting. So therefore, to prevent overfitting, there are a couple things that you can do to regularize. So first, you can actually add, let me give more context on regularization. So as a neural network learns, neuron weights start to settle into their context within the network. This is actually really interesting and has been shown through, if you were to ever like go into the weeds or look under the hood of a neural network, you'll actually start to find, especially with more complex problems like images or deep text data, you'll start to see patterns of, okay, this group of neurons is learning to identify patterns or textures in an image. And this one is more about like recognizing edges. And these neurons are more about recognizing colors. That actually does tend to happen, especially when you have very, very complex input data. So that's what it means by settling into their context within the network. So weights of neurons are tuned for specific features, providing some specialization. So as I mentioned before, those neurons will be specialized into identifying certain parts of your input data, which is super cool. One downside is neighboring neurons can become too reliant on this specialization, which if taken too far, can result in a fragile model too specialized to the training data. So for example, if you've seen those instances and imagine that you are trying to classify wolves and dogs. That's actually like, I think a pretty common, I forget if that's exactly what it is, but you can train a neural network to classify wolves and dogs, which they're part of the same biological family, I think, I don't know. But classifying wolves and dogs is one of the common problems that people like to use as an example, because ideally you start to recognize, okay, this is a dog's face, body, fur versus a wolf's face, body, and fur. But some very similar experiments have been done where instead of recognizing or learning things about the animal itself, it starts to pick up on other patterns that you don't want it to pick up on in the training data. So for example, dogs are often photographed in like houses or like people's yards, whereas wolf photos are more taken in like the forest or like really, really like the wild, basically. And so there have been examples where you start to see that your neural network is actually focusing on that. So if you had like a wolf in a house, for example, it might actually classify it as a dog. And if you had a dog in like the great wilderness, it'll classify that as a wolf. So that's just, yeah, that's basically your neural network learning the wrong details, because it's very hard to get your neural network to, it's very hard to tell it what to focus on, and it doesn't know what is relevant and what is irrelevant information to focus in on. So that's what it means by too specialized to the training data or becoming too reliant on a specific specialization that might not be the most relevant thing to us as humans. So this reliance is basically referred to as complex co-adaptation. So the fact that a neural network that's supposed to be trained to identify dogs and wolves has now kind of been trained to instead recognize like domestic scenarios or environments versus like wilderness, you know? So yeah, complex co-adaptations. So methods that you can use to regularize. You can actually add L1 or L2 regularization within each hidden layer. So within every layer here, you can actually add a regularization parameter. I don't know, I haven't run this notebook, so I don't think, yeah, I don't think it'll show over here, but I think I have one. Let me see if I have it later on. I don't think so. Yeah, I don't have that either, but in one of your labs, it actually has that included. So you can add L1 or L2 regularization within each hidden layer. If you remember, L1, L2 is basically like our lasso and ridge, where for L1, it'll actually drop some neurons to 0. So it'll actually make your neural network a little bit lighter. And then L2 is basically, again, penalizing heavy, high coefficients in the exact same way that we did with ridge and lasso, actually. Another more direct way of regularization is a dropout layer. And dropout layer basically means that you can add a layer within your neural network. So for example, with this one over here, between this and my second hidden layer, or maybe even this and my last hidden layer, I can add what's called a dropout layer and tell it, okay, out of all the neurons or out of all of the parameters from that layer, let's only look at a specific proportion of that. Actually, it's kind of like bootstrapping if you think about it, or no, not exactly like bootstrapping, like subsetting, I guess. So as an example, let's say I want to put a dropout layer between this and this layer. And this first layer has 108 parameters. From this to that layer, if I put a dropout layer of like 0.5, for example, and I'll show you all the syntax for that in a bit. If I have a dropout layer of 0.5, that means I will randomly pick, what is it, 54 parameters to look at. 54 parameters I'm just going to completely ignore. And that's how dropout works. And that does help with not overfitting. So the syntax for that, oh, yeah, that's a meme of Thanos using dropout. But yeah, dropout is a technique where, again, randomly selected neurons are doing training. Dropped out randomly means that they're contribution is temporarily removed in the forward pass and weight updates are not applied on the backward pass. So backpropagation will not occur for those specific neurons. So dropout layers will basically look like this: model.add dropout, and then you just give it whatever number you want. I think I have that in the model later. Do I? Okay, I guess not this one either, but dropout is definitely in your curriculum as well. Okay. Another thing that you can add is something called early stopping. It's not technically regularization, but it's something that you can actually put in your model in one of its, when it's, I think it's in the compiling step, so that your model doesn't overtrain. The syntax looks like this. You will add a stopping monitor, and you can put stopping monitor, which is a variable. You can put the stopping monitor when you compile. I forget it is if you compile or when you fit your model, one of those. But basically what this means is if you see your train and test metrics diverging, or if your train metrics or if your test metrics are not improving anymore, you just stop your model. So what this means is, and patience equal to 2 basically is how many epochs you will wait for it to stop training. So for example, if we look at this example over here, let's just say that if we zoom in here, you can see that our train and test start to diverge after like about 100 epochs. So let's just say after 100 epochs, our test accuracy on average doesn't actually go up. If I set patience equal to 2, that means at epoch 102, your model will just stop. It'll just see like, okay, any further training doesn't seem to be improving my model. Let's just stop here. You can play around with this patience number as well, because you can see here, I mean, this data set that we use to train this model is very small, so it's very, very sensitive. But as an example, if you set patience equal to 5, you can see maybe it continues to go up a little bit, maybe it doesn't, but setting that early stopping and patience, even if you set 300 epochs to train, and that was something that I set up, let me zoom out. Yeah, that's something that I set over here with the model fit step. Something I set with the model fit step, even though I set 300 epochs, it'll automatically stop once your testing metrics or training metrics stop improving. That's something that you can do as well. And you can actually define your early stopping parameters based on any metric you want. So you can actually have it look at your accuracy, you can have it look at your loss function as well. So yeah, that's cool. So that's not exactly regularization, but it's another way to combat overfitting. So those are all the main things that you can tune in your neural network. Again, on Friday, I'm going to show you all how you can do grid search. For example, you can run a grid search where you test like different activation functions. You could even test different number of nodes. You can test different values for like dropout, for patience, things like that. And I'll show you all how you can do that on Friday. Any questions about all of these hyperparameters before we move on to some image stuff? Okay. So you can actually run image classification with a regular dense neural network. I think even like somewhere here I mentioned that like for image classification without convolutional layers, you'll just need dozens of dense layers. And how you would do that with an image is you would actually take all of the pixels and flatten them out into one long vector, and you can use that as your input into a dense neural network. And I do believe that the first lab that deals with image classification actually does that method. You're doing it with just a regular neural network, the same neural network that we use on this data set, maybe with more layers, with more nodes, so on and so forth. However, what is more efficient, in my opinion, for image classification is adding convolutional and pooling layers. So to preface again, how a machine can actually interpret image data. Again, remember, every image is represented as a matrix or a tensor. If it's a black and white image, it is a matrix that matches the dimensions of how many pixels there are. And the value of each value in that matrix represents the intensity of gray in that specific pixel, and put together, that's how you get like a grayscale or black and white image. For color images, it's a tensor of 3 matrices of the same dimensions, one for the redness, one for the green, one for the blue, and put together, it basically outputs an image. So that's how a computer reads images, and that's something that we can make use of by using these layers. So if we were to flatten everything out, not using any of these new layers that we're going to talk about, if we wanted to throw an image into a regular neural network, you can imagine that some information is lost, right? The fact that you're taking like every row of pixels and you're just making it into one long string, one long line, you kind of miss out on the patterns within the image that occur over more than one row of pixels. So that's where convolutional layers and pooling layers come in. Cool. So a convolutional neural network, or a CNN, is any sort of neural network that has convolutional layers. So it's just a new kind of layer that we're going to talk about. Now, CNNs are mainly used for image recognition and classification because of the 2D nature of images. They can be used for video analysis, NLP as well to some extent, and speech recognition if you want to look at waveforms, which can be interpreted as images as well. So think about how our brains see an image versus how a computer sees an image. So if we are trying to discern between dog and muffin, blueberry muffin in this case, if we see like a fluffy tail, wet nose, flappy ears, good boy, we can conclude that we're seeing a dog. There's not one singular thing about a dog that our brain recognizes as a dog, but rather it's an amalgamation of different patterns that allows to make a probable guess, right? It's like a combination of, okay, we see the eyes, we see the nose, we see like the dog shape. That's how we recognize something as a dog. That's how we know that like this first image is not a dog, because that's not a face. But if you think about how computers see images, again, with like what I was saying before, it is represented by a tensor. So color images are a 3D object, like I was saying before, comprised of 3 matrices, one for each primary color, that can be combined in varying intensities to create different colors. And every element in the matrix represents the location of a pixel and contains a number between 0 and 225. Indicating the intensity of the corresponding primary color in that pixel. So at any color image, if you zoom in to any like 3x3 pixel, 3x3 square in any image, you can actually break it down and it looks something like this. And these numbers represent the intensity of blue, green, and red, and they're kind of just layered on top of each other. So therefore, we have to think about convolutions. So in English, convolve just means to roll together. And CNNs just make use of kind of linear algebra to identify patterns using pixel values. So how CNN works, instead of just looking at every pixel individually, it takes a look at groups of pixels together. And this is what helps it maintain like any sort of pattern or any sort of pattern or trend that exists over a single row of data, over more than a single row of data. So what it does, it actually takes a small matrix and moves it across an image and multiplies that together every time it moves. So this is actually really good. This is pretty much exactly what a convolutional layer is doing. It's kind of like starting at the top left, and you can sort of define how big you want this middle matrix to be. So you define how big you want this middle matrix to be, and you're just going to roll this small matrix over 3x3 parts of the image. And the number that results here is just an element-wise multiplication between this small matrix and whatever it is projected over. So what's cool here is this is actually something that helps it identify patterns such as textures, edges, colors even, shapes, so on and so forth. So this small matrix is known as a kernel or a filter. And each one is designed to identify a particular pattern in an image. So when a filter is rolled over this image, the resulting matrix is a feature map. So this blue result over here is a feature map, which is literally a map of where each pattern of feature is in the image. Basically, elements with higher values indicate the presence of a pattern that the filter is looking for. Now, how do you tell the kernel what thing to look out for? It actually does that on its own, which is really, really neat. So the values in this kernel are adjusted by itself during backpropagation. So it's actually going to do a bunch of random things first, and it's slowly going to learn, okay, for this particular data set, I'm going to look out for edges. or like vertical edges, maybe as an example, to kind of discern between my two classes, for example. Maybe if you're looking at classifying something like shapes, let's say you want to classify just pictures of circles and pictures of squares, it's going to look for straight edges versus curved edges. And that's something that this convolution or this kernel filter can figure out on its own, which is what one makes it take a very long time to train, but also what makes it very, very powerful. So when you're defining a convolutional layer, and I do have an example below this, you'll see, there are a couple things that you want to adjust for. So one, the padding. I mean, the first you have to tell it the dimensions, which is given. We'll see that later. But also you can give it the parameter of padding. So padding is literally what we see over here. You see how, let's just say the image doesn't really start until the second column and the second row from the bottom. You want to pad it with a layer of zeros. And this is just so that it doesn't lose information on the edges. So yeah, it's just giving a padding of certain number of values around the edge of the image such that you don't lose the edge information. So yeah, helps detect patterns at the edge of an image. Next, you also can define the stride, which is the number of pixels to shift the filter on each roll. So this over here, because it's always shifting by 1, has a stride of 1. If your convolution is bigger, so let's say your convolution, you choose to do like a 6x6 matrix kernel filter that's rolling over the image, maybe you don't need to do a stride of 1. Maybe you can have like a stride of 3, so it makes its way across the image a little bit faster. So yeah. The larger the stride, the smaller the feature map will be, but you'll lose more information. So it's a little bit more efficient, but you lose more information. So any questions about convolutional layers first? Okay, so again, convolutional layers is one of the first layers that we deal with so that you can actually look at your data in 2D, which is what makes it so special. On top of that, there's also pooling layers. Usually when you have a convolutional layer, you feed it into some sort of pooling layer. And there's different kinds of pooling layer, the most common being max pooling. And I think you'll see me use it here. So you see how I have like a max pooling 2D layer. And what that will do, it'll help to reduce your feature map to things that are important. So like convolutions, the method is applied one patch at a time. And max pooling just takes the largest value from each patch of an image and then places it into a new matrix next to the max values from other patches and discards the rest of the information contained in the activation maps. So let's say that after your convolutional layer, this is what you get here. Like this result corresponds to this. You add an extra pooling layer over this so that it can pick out the relevant parts. So for example, let's just say that this is used to identify fuzzy textures. And the bigger the number, the more prevalent fuzzy textures are. So from this pooling layer, it will say, okay, this area has a value of 6 for fuzzy textures because out of this red area, it's pulling out the 6. Out of this is pulling out the max value, which is 8, pulling out 3, which is the max value here, and pulling out the 4. This is max pooling with 2x2 filter with stride 2, which is why it's doing it this square, this square, this square, this square. You can also do it with a stride of 1 to get more granular information, but it will take longer as well. So things to play around with. So you can do max pooling. Other methods also exist. For example, average pooling is a kind of layer that you can use as well. What pooling does is it basically tries to cut out the noise as much as possible for your neural network, especially because you're working in 2D data. It can be very intense for your model. It's very, very computationally heavy. So you want to get rid of as much noise as you can using some sort of pooling. So this results in a new feature map with reduced dimensionality that is then passed into another convolutional layer if you're doing multiple to then continue the pattern finding process. So these steps are going to be related and repeated until they're passed to a fully connected layer that proceeds to classify the image using the identified patterns. And I'll show you all what that looks like when you actually implement it in a little bit. So the last thing we have to talk about is flattening. So in any CNN, because we're looking at our data in 2D, there's usually a flattening component where you have to flatten your data from 2D to one-dimensional so that you can actually get your classification results, because your classification result is it's a number or a vector if it's multi-class, or regression, it's going to be a number as well. So basically, once the neural network has collected the patterns, the series of patterns, it's ready to make a guess as to what it is. So you have to first flatten the 2D matrix into a 1D vector so that it can be passed into a normal densely connected layer for classification. Then using this vector, you can make the prediction as to what the image is. So if you're doing any sort of image classification, I do highly recommend using a combination of CNN layers or a combination of convolutional layers and pooling layers, because you can sort of imagine like looking at your picture in 2D is just going to be a lot more effective than taking your image and turning it into like one long string of pixels. Any questions before we get into implementation? Okay, so I've already run this notebook and you'll see why, because some of the processes take a little while. And what we're doing here is same, we're using Keras. Oh, by the way, like you might have to pip install either Keras and or TensorFlow to get these to work if anyone's having issues. People who are using GPUs seem to have issues with this, so let me know if you run into any issues with that. If not, you can always use Google Colab because their systems are fine. So I'm loading in a data set from here. And this data set is actually a 10 class image data set with images. I don't even know the classes in this, but there's a bunch of images. You can see that there's like animals in here, cars, trucks, boats, so on and so forth. I forget the categories there are, but there are a lot of images in here, and it's 10 class classification. So that means if we randomly guess, we're going to get roughly 10% accuracy rate. Now, what I'm doing here is I'm just inspecting my data. I'm loading, this is one of the pre-built data sets or the preloaded built-in data sets. And what this shows me is the shape of my data, which is a little bit harder to read than what we're used to, because prior to this, all of our data was rows and columns, right? Your columns are your features, your rows are your data points. For images, it's slightly different. What this means is every image is 32 by 32 by 3. So that means each image is a tensor that is 32 by 32. As you can see here, each image is 32 pixels lengthwise and widthwise. And then 3 because one red, one green, one blue layer. And here we have 50,000 of these images. So when you're reading the shape of your image data array, it will have 4 dimensions. Basically, the number of images that you have, the dimensions of your image itself. For tests, we have 10,000 of the images of the same shape. Take a look at my value counts. They are all equal. Okay, so this is a very, very simple CNN. Having only 2 sets of convolutional and pooling layers is actually very, very light for a CNN. So you'll actually see that this does not perform very well. I only have it running for 5 epochs, as you can see with my last data set, even though that data set was very easy, or that data set only had 8 columns. The fact that I ran it for 300 epochs and it only started to properly fit after roughly 100, this is going to take much longer. We don't have time to like sit here and watch this run. Anyways, you can see here, it is still a sequential model. It's still a sequential model because it's forward feeding. The data always just goes through the model. It's not like a time series sort of model where it has to like look back at prior dates as well. So it's still a sequential model. And for image data, you usually just start right off the bat with your convolutional layers. So with this convolutional layer, what I'm doing here is I'm defining my convolution. So I'm going to have 64 nodes that take care of 3 by 3 kernel filters. So 3 by 3 is my kernel filter, activation function prelude, and my input shape, I have to give it the shape of each image. But this is a number of nodes. This is the dimensions of the kernel filter. And then they're usually followed by some sort of pooling layer. Here I'm just using a 2D max pooling with 2 by 2 max pooling convolution. And I'm just doing the same thing over and over again. That funneling down technique still holds for CNNs as well. So you can see I start at 64, I go down to 32. And then to go from 2D to 1D, I flatten out all of my data. And then I can then feed it into a dense layer, because your dense layers cannot recognize your dense layers don't recognize 2D data, basically. So I have to flatten it first. I'm going to put it through one more layer of a dense, one more dense layer. And then I have my, my categorical layer. So from here, if I run this, and actually if I take a look at CNN.summary, you'll see how many parameters we're training. So in this model, we are training almost 60,000 parameters at the same time. So I'm going to run this in a little bit, but I'll also look at the results later on. When I run this, you'll see that it is a much slower training process as what we were seeing compared to what we were seeing yesterday. Yesterday was pretty much immediate, but when I run this, you can see that it is running all my data like that. So I set my batch size to be 500, and because there are 50,000 images, it's running 100 batches of 500, and it's feeding all of my data through that. Once this finishes, that will be one complete epoch. So my neural network would have seen all of my images one time. And that I think takes roughly 20 seconds. Yeah, 22 seconds over here. And right now I have an accuracy of like 9% and a validation accuracy of 10%. And because this is very, very slow right now, because there's so many images and we have 60,000 parameters, this might take a while. So for those of you doing the image classification project, prepare for that. Things that you can do to make it faster. If you think that color is not very important, you can actually grayscale your images so that instead of a tensor, it becomes just a matrix. In your labs, there is one parameter. If you go to your CNN labs, the flow from directory library, if for those of you who haven't gotten there, never mind. But there is an option that you can actually turn your image into grayscale. And I know for the provided data set, it's X-ray images anyway, so the color shouldn't matter. So you can totally do that to speed up the process. So as you can see here, still training. I only put 5 epochs here, but you can imagine if I wanted to do like 100 or 300 epochs, I'm going to leave this training for a while. I actually did image classification for my own phase 4 project, and I let my computer run plus grid search and all that overnight. So maybe expect to do that. I don't know. All right, so this is running, but as you can see here, the loss function is nan because it's just not doing well at all. So I'm not going to rerun this, but it's evaluating my train and test metrics. My train metric is 10%, test metric also 10%. So not doing very great. If you train for longer, it will do better. And same as yesterday. I mean, these graphs won't show much because we don't have time to do all of the model training the way that you should, but yeah, you can get the same graphs that we did yesterday. Ideally, it will look a little bit more similar to this. All right, so image classification is it is difficult to do it well. So for this project, I'm really only expecting to see some tuning and more of the process, because neural network tuning can take a very, very long time. So I really just want to see setting up of neural networks and the overall process of how you evaluate. I have linked here a walkthrough, and this is a really good resource because it basically goes through like step by step how they go from a really awfully performing network and the things that they added to make it get better and better. So tomorrow we're going to talk about the project as a whole, and I'll give a little bit more guidance on how y'all can work together, especially in those of you that are in teams of 3, and how you can better collaborate on this project, because I do want this to be as breezy as possible leading into your capstone. But tomorrow, on Friday, we're going to talk about pre-trained networks, which are pretty cool. It's kind of similar to how when we were dealing with word embeddings last week, these the word vectors are already created for you. There are some networks that are already pre-trained to recognize certain things in images. So we'll talk about that. We're also going to talk about recurrent neural networks, which is basically the set of networks that are more for time series data or anything that's related to forecasting or text prediction. You can also use a recurrent neural network, which is cool. We're also going to talk about grid search for neural networks and also saving your models. So you can save your models such that every time you want to close your notebook, or if you want to use your model in a brand new notebook because you don't want to rerun everything again, you can save your model. Very similar to pickling, but there's a slightly different process for neural networks. I'll talk about that on Friday as well. But yeah, at this point, any questions? All right, please reach out to your project partners today. If anyone hasn't heard back from anybody else, please let me know as soon as possible, hopefully by today, if not by tomorrow when we talk about the project. Cool. Any final questions before we close out for the day? Going once, going twice. All right, again, I recognize that this is a lot. It is very, very intense. The StatQuest series on backpropagation is actually a really good one if you really want to understand neural networks, but I totally understand that like now might not be the best time to get into like the nitty gritty of how exactly it's working. My philosophy is you can start with implementation and then your understanding can always catch up afterwards. All right, well, if there's nothing else, I will see you all back here tomorrow to officially kick off our phase 4 project. We only have a week for this one. But yeah, anything else, feel free to Slack me. Let me know if you all have any questions at any point. Bye, everybody. Have a good rest of your day.